Finished last time by talking about the Bronsted-Lowry theory, where we have the idea that acids are proton donors and bases are proton acceptors. And a neutralization is only a reaction that allows a transfer of a proton from one species to another species. We looked at the idea of conjugate acids and base pairs because of the equilibrium reaction. We see that a species, when the reaction is going from the left to the right, the species is this species is donating a proton and forming fluoride minus, and this one's accepting it. So this one, HF is an acid going in this direction, and the water is the base. Going back in the opposite direction, this one, when it collides with that, will actually reform the molecular acid, and it will be, this one, when it's doing that, is acting as a base. So that makes this an acid-base pair. Water, the self-ionization of water helps us to explain a neutral solution. In a normal neutral solution, there will be hydrogen bonding between this lone pair and the hydrogen on the next molecule of water. Very occasionally, that becomes so strong that it actually takes the entire hydrogen off there, and it leaves this as OH minus, and this is H3O plus. And that's an interaction between two water molecules. So because they're forming, and the H plus and the OH minus are forming at exactly the same time, they're in equal numbers in water. And it happens with a frequency of 1 in 10 to 10 million, which means that if you're looking at the pH, that's 10 to the minus 7. So the pH is 7. When you put a strong acid into water, it dissociates into ions completely. So immediately it hits contact with the water molecule, there'll be a transfer of the H from the Cl onto the water molecule, and at the end of the reaction, it will have gone completely into the form of the anion and the H3O plus ion, which we just write as H plus most of the time. All right, so yes, the chlorons were left, the chlorine took the electrons, and the proton, the H plus, was associated with the water molecule. Notice there's an arrow there that means it's a one-way street. It doesn't go back again. It's a reaction that goes to completion. So when these two touch, there's a complete transfer of the hydrogen ion, and it's not going back again. And when that occurs, when you've got hydrochloric acid going in there, your H3O plus or your H plus ion concentration is much higher than your OH minus concentration. And the result is that the pH is more acidic. For a base, a strong base like sodium hydroxide, you dissolve that in water. These are now free ions in the solution. So when you drip that into here, those free ions in the solution increase the concentration of the OH minus ions and decreases the concentration of the H plus ions, and the end result is that the solution is basic. With a weak acid, this is where the Bronsted-Lowry theory comes into its own, because it allows for the reaction to be going in both directions. You're not only saying that this one is an acid when it goes that way, but this species here is an acid when it goes in the opposite direction. So the reaction goes in both directions. So when the acid molecule hits the water molecule, it will transfer an H plus. But when those two hit each other again, when the hydronium ion hits again, it will return the H plus. and it will reform the molecule. Now, the HA does not in any way change the pH. It is only the hydronium ion concentration that changes the pH, not the HA. That doesn't affect it at all. So over here, you've got the acetic acid molecule, and the water molecule comes close to it. There will be a time while one bond is breaking and the other one is being formed, and then you'll have the acetic acid anion and the H plus ion, or the H3O plus, the hydronium ion over here. Now that's fine, but as soon as these two touch each other it'll be going back the other way and reform the molecule. And the molecule does not change the pH, only this does. So however much of this remains at equilibrium will be the thing that influences the pH, and it's a very low amount. Similarly for weak bases, when you've got a water molecule approaching an ammonia molecule, the lone pair here becomes attracted to it. It takes that hydrogen off, so there'll be a bond forming and a bond breaking. And then as that does, this becomes NH4 plus, and that becomes OH minus in the solution. And that OH minus, it does affect the H plus ion concentration, because it'll react with the H plus, it will lower the H plus ion concentration,